Welcome to the overview of Digital Logic, Computer Architecture, and Dev Containers, supporting schools from little to large. The intent of this project is to bundle together all of the resources needed for a contemporary course in digital logic and computer architecture into a single developer container that can easily be adopted by anyone teaching such a course and can quickly be set up by students who are in such courses. So the overall development container can be run completely from the web in a code space with all of its functionality. So we'll do a quick overview of that, and then a tour through a handful of the features that the Dev Container supports that I've recently used in my course in digital logic and computer design. Hey, an overview of the process of starting up the Dev Container. So we're going to create a code space. And it takes approximately 2 to 4 minutes to set up. The Dev Container contains nearly everything you might need for a modern course in digital logic and computer architecture. In this case, I've provided tasks that correspond to each module of the material. So fourth module is about hardware description languages, where the students have to create a behavioral model for a full adder, amongst other things. Using the Dev Container and open source extensions, in this case Digital.js, they can actually simulate the behavior of the various sorts of digital logic artifacts that they've created, and actually get a sense of how they behave in real time. In addition, they can actually run full hardware test benches, and they can view the results of the device under test, like they can see inputs A and B being added together and producing a sum and a carry out, and they can actually zoom in on traces and confirm that things look correct. Then when we move on to more complicated circuits, they can actually create a multi-bit adder that uses multiple instances of that full adder. They can again simulate it, and here the simulator, Digital.js, happens to show the full adder modules that were created in the previous unit of material. They can interact with it and see multi-bit numbers being added. They can run, again, a test bench and confirm everything behaves correctly. And more than that, they can actually see how it would be mapped onto modern FPGA architecture. So in this case, it will be mapping it onto a device called the ICE40, and this shows the structure and the number of lookup tables that are going to be used on the ICE40 and the basic overall mapping onto the architecture. And then, more importantly, they can actually create a bit stream to run on the architecture. So I'm going to go ahead and generate that bit stream, and I'm going to open up an FPGA programmer. When I do this, it'll ask me to open up in a browser. I'm going to go ahead and connect to my hardware, where I'm using the Upduino, approximately a $35 part, and this interface board, which runs $2 to $10, and provides 8 7-segment LEDs, 8 buttons, and 8 LEDs. I'm going to go ahead and upload my example onto this. So in this case, I've organized the hardware into 2 sets of 4 buttons. Each set of 4 buttons corresponds to a digit. So I can have a 1, a 2, a 4, a 5, an 8, and so on, A. And it adds it to the second digit, which is the rightmost set of 4 buttons, and shows the result over on the right. So 1 plus 1 is 2. Okay, in addition, we can use a variety of open source extensions to support things like simulating assembly languages. In this case, there's an example of a RISC-V assembly language program, and we can actually run that in a simulator, and the simulator even provides a 7-segment set of 7-segment displays, a couple of LEDs, and a couple of buttons. So I'm going to simulate I'm going to run this assembly language, which is a simple program that controls a counter that either counts up or counts down. Finally, when we move on to the full computer architecture segment of the course, students can actually complete a full model of the RISC-V single cycle CPU designed by Harris & Harris. They can extend it with additional instructions, test out those instructions in a variety of test benches, and finally actually run their counter program from the previous module on their actual hardware using their updated processor design. So overall, this development container contains nearly everything you would need to both work with hardware description languages and to work with RISC-V assembly language and to combine the two